Hey there, welcome back to 2241. This is the examples 2 video for section 2.2. We're going to do some more curvature and then some tangent, normal, and binormal stuff. All right, so fifth problem, I guess. Find the curvature of the parabola y equals x squared at these 3 points, 0, 0, 1, 1, and 2, 4. All right, so how do I do this? Well, there was another formula for curvature, and you can get it from the formula we just used in the last video at the end. But I'm just going to write it down here. So curvature as a function of x for a planar curve. So this is a planar curve. It's in the xy plane. Is given by this formula. Take the absolute value of the second derivative and divide that by 1 plus f prime of x squared. I don't love those parentheses. Squared all to the 3/2 power. Okay. So the 3 comes from the cube in the bottom of the other curvature formula. The 2 comes from the fact that we're looking at a norm. And this is the tangent vector. Okay, so what do we do here? Well, I have things in terms of x. I need a vector function to work with. And this is going to be parameterized just with x as the parameter. Well, then the second coordinate is just x squared. Okay, so f of x is x squared, and now I just need to find f prime and f double prime, plug them into kappa, and we'll be good. So f prime of x is 2x, f double prime is 2, and we can pop them right in here, and we get absolute value of 2 divided by 1 plus 2x squared to the 3/2 power. And if I simplify this a little bit, I can't do much, but 2 over 1 plus 4x squared to the 3/2 power, and I have a sum there, so I can't distribute this. So I'm just stuck with that. All right. Now I want curvature at certain points. Well, since my parameterization is just x on the x squared, it's in terms of the axis variable, I can just plug in 0, 1, and 2, and I'll get out exactly what I need. So we need kappa of 0. That's going to be 2 over 1 plus 0 to the 3/2, or 2. Kappa of 1 will be 2 over 1 plus 4 to the 3/2, and that'll be 2 over square root of 5 cubed, so 5 root 5, and kappa of 2 is 2 over 1 plus, all right, now I have 4 times 4 is 16 to the 3/2. And somewhat annoyingly, this will never end up giving me a square, I think. We have 2 over 17 root 17 for the curvature. All right, note the curvature is getting very, very small, and that should make sense. A parabola looks like this, sort of. Mix it up a little. And as we go further out from the vertex along the curve, this looks more and more like a straight line. The tangent circle at that point would be very, very large and have very, very large radius. And then the radius being large means the curvature is small. Whereas our maximum curvature happens right here with a curvature of 2, which would mean a radius of 1/2. Okay. Next up, we want to find the basis vectors of the Frenet-Serre frame for the circular helix. All right, so this sounds maybe a little complicated, but we know the equations for a circular helix. We'll write those down. Three, three, two, one. Right, now that these are written down, we need the tangent, normal, and binormal vectors. All right, and this is just a process that we work through a little bit at a time. So tangent is r prime divided by norm of r prime. All right, r prime is minus sine cosine 1, and norm of that is going to be square root of 2. You can check that if you want, but there's our tangent vector. Our normal vector is the derivative of the tangent vector, t prime, divided by its norm. Okay. And so the derivative of the tangent vector is going to be, well, we're going to have this root 2 out there, and I'm going to put that in front. So 1 over root 2 times vector minus cosine of t minus sine of t, and then 0. And then I need the norm of this. So the norm of that 1 over root 2 is just going to be 1 over root 2. Norm here is going to be square root of 1. So I need to divide by 1 over square root of 2, which means that these just cancel. And my normal vector is minus cosine of t minus sine of t, 0. And this should make some sense. The normal vector is always going to point towards the center of the helix, or the axis around which it's rotating, because it's kind of like a stretched out circle. All right, last is our binormal vector. And remember, this is just t cross n. And we have t, we have n right here. 3, 2, 1. All right, and now that we've got our cross product set up, we just have to compute it. So cosine times 0 is 0, minus 1 times negative sine. Okay, so we'll have sine, and this 1 over root 2 I'll just keep out front for later. So our first coordinate is sine of t, and then our second coordinate is going to be minus cosine times 0, or minus 0. So we just have minus cosine t. And then our last coordinate is sine squared minus negative cosine squared, or 1, using the Pythagorean theorem. And there is our binormal vector. Okay. So we have our TNB frame given by these these 3 vectors. The reason that the tangent and binormal vectors have that 1 over root 2 factor is because they're pointing at 45-degree angles to the xy plane, or the z-axis. And so you need that 1 over root 2 to compensate for the length. Okay. And that's it. So we have our T and B's. Next, find equations for the T and B coordinate planes and our O of the helix at this point. 0, 1, pi over 2. Okay, so we have our T and B vectors, and we remember maybe that maybe we don't remember, so we should write it down. The normal plane is orthogonal to the T vector. The rectifying plane is orthogonal to the N vector, and the osculating plane is orthogonal to the B vector. So I wrote these in order T and B and RO to make things a little bit easier. Hopefully easier to remember. All right, so if these are the vectors normal to each of these planes, then we know how to write down the equations. We simply use them in the little n dot, do that in yellow actually, little n dot r minus r0 equals 0 equation. That's our vector equation of the plane. And we have a point on the plane already, so we know what to use for R0. So we'll use this as R0. I'll just say that. We'll use this as R0. Okay, so then we have, what is our T vector? So our T vector is 1 over root 2 times the sine of, okay, what T value does this correspond to? Well, note that last coordinate is T based on this vector equation. And so our T value is pi over 2. So we have sine of pi over 2, comma, cosine of pi over 2, pi over 2. Sorry, our T vector should be not that, but minus sine of pi over 2, and then cosine of pi over 2, comma 1. There's our T vector. Dot x minus 0, y minus 1, z minus pi over 2. And this is equal to 0. Okay, well, we can ignore that 1 over root 2 by just multiplying both sides by root 2. And then sine of pi over 2 is 0. Cosine of pi over 2 is 1. Oh, other way around. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. And then we just have our 1 coordinate right there. So we get, in this dot product, minus 1, comma 0, comma 1, dot x, y minus 1, z minus pi over 2, and minus x, the y part goes away because we multiply by 0, and then plus z minus pi over 2 equals 0. And so the equation of our plane is z minus x equals pi over 2. All right, so that's our normal plane. What about our rectifying plane? Okay, so we need our normal vector now. And this one is a little bit easier. It's minus the cosine of t times the minus the sine of t, and then 0, dotted with the same thing, x, y minus 1, z minus pi over 2. All of these planes have to go through the same point. We're using that as the new origin here. So this equals 0. And again, t equals pi over 2 here. So we get 1, 0, and this is even easier, 0, -1, 0, dot x, y minus 1, z minus pi over 2 equals 0. This one is parallel to the xz plane, I believe. Yes. Meant to write this out. So we get negative y minus 1 or 1 minus y equals 0. And so that tells me that y equals 1 is the equation of my rectifying plane. All right. Last is our osculating plane. And this one, I remember, is going to have a 1 over root 2. And we'll use b as our normal vector. So sine of pi over 2 minus cosine of pi over 2. And then I believe that's a 1. Yes. And dot x, y minus 1, z minus pi over 2, just like before. And these, as usual, 1, 0. And we get, oh, and we can ignore that 1 over root 2 by multiplying it over. So we have 1, 0, 1, dot, all this stuff. All right, and now this is almost like the normal plane, except we don't have a negative x. We have x plus z minus pi over 2 equals 0. And so our osculating plane is given by x plus z equals pi over 2. All right. And so those are the equations for the t and b coordinate planes. So all we really needed to do was find t, n, and b, and then we use those as normal vectors to the planes with our standard vector form for a plane. Okay. Last is that we want to find the equation of the osculating circle for y equal x squared at 0, 0. Okay, in general, the equation of the osculating circle can be very difficult to find. But for this problem, 0, 0 makes things very easy for us. Okay, so what do we need? We need the radius of a circle and the center. Okay, well, the radius, if we have the radius, and we know that the curve has to be tangent to the parabola, let's draw our little parabola here, give ourselves a visual, some visual intuition. Okay, so here's our parabola, and our osculating circle is going to have to be tangent to the curve right there at the origin. And so we want the radius, which is going to be the distance from the origin to that center point. So once we find the radius, we can figure out the center because we know that this point is 0, 0. All right, well, how do we find the radius? Well, remember that the curvature at 0 is 1 over the radius at 0. And the curvature we have a formula for. So again, if we parameterize with x as the parameter, we have this, and then our curvature formula says, all right, absolute value f double prime over 1 plus f prime squared to the 3/2. If we go through this, we remember from before that this is 1 plus 4x squared on the bottom to the 3/2 with a 2 on top. And we need the curvature at 0. Okay, so kappa of 0 was 2. Okay. So our osculating circle radius, R0, is 1 over 2. Okay. So we now have our radius of this circle, which is right here. So R0. All right. Well, the circle is supposed to be tangent to the curve, and that means that the normal vector to the curve is pointing straight up, and we need a point 1/2 away, so we simply add 1/2 to this coordinate. So our center at 0 is 0, 1/2. All right. By the way, computing this center is why finding the osculating circle can be a real pain in the butt. Okay, so there's our, those are the only things that we need for the equation of a circle. Now we can write down the standard form, x minus 0 squared plus y minus 1/2 squared equals the radius squared. So we have x squared plus y minus 1/2 squared equals 1/4. And there's the equation of our osculating circle. So this one was fairly easy. All right. And that's it for our worked examples for 2.2. There should be some homework on the page that will help you get started with some practice.